Hi there. In this video, we're going to talk about conservative vector fields. Before we explain what a conservative vector field is, it's important to revise what a line integral is. So you can go back to the previous videos and rewatch them and understand how we evaluate line integrals. But very generally, line integral is just integrating along some curve of some vector. It could be, for example, f with dr. In the examples in the videos previously, we saw that analogy of this would be work done. So a vector could be something random. We could take an example to be f is equal to 2xyz in the direction of I plus x squared z in the direction of j and x squared y in the direction of k. So dr, as you would recall, is simply just dx I plus dyj plus dzk. And in the examples that we had done previously, we saw that we can evaluate dr to be along some curve, and it could also be parameterized. We could evaluate this along a parametric curve. So why do we want to understand what a conservative vector field is? Well, firstly, because conservative vector fields has applications in physical systems. So if we want to understand physical laws underlying some kind of system or whatever it may be, an example of this could be conservation of energy. Conservation of energy. Another application of conservative vector fields is when we want to simplify calculations. If we see that a vector field is conservative, often it's the case that we can our calculations become much easier than what we thought they were going to be. So this would be, for example, in work done in gravitational fields. So what do we mean when we say a vector field is conservative? All that we are saying is that if we have two paths from A to B, and we want to evaluate the line integral along these different paths to get from A to B. There could be one way is how I've just drawn. We can call this C1, and we could have another path from A to B along some other curve, call that C2, and then there is another path, maybe C3. So we can evaluate the line integral along these different paths. So if a vector field is conservative, what it means that the line integral along each of these paths are the same. So if we were to take the integral along C1 of f dr, it would be equal to the line integral along C2 and it would be also along C3. So what does this mean? It means that if we go along the path from C1 to A to B, and then if we go back along another curve, it means that the work done would be the same going from A to B and then going back from B to A. So how do we check if a vector field is conservative? Well, there's three tests. There are three tests. The first test is simply just to integrate along the path. So the first test is just to literally check the integral along between the paths. So we have A to B here, and then we integrate along the path from A to B. And then if we integrate from B to A, going back, these things should be the same. So if we look at our previous videos, we'll see that there was one particular video that spoke about the integral along a closed curve, right? So we integrate this region between these two curves, okay? So it looked something like an integral with a ring around it. So it was the integral along a closed curve. So if we integrate the integral from a to b. So if we integrate between a to b of our line integral, it should equal to the integral from b to a. So what does that mean? It means that the closed integral, the integral along this curve from a to b and back to a of the line integral is actually equal to 0. So that's the first check. The first check is integrate from a to b and then b to a, and then add the two together, and then you should get 0. So that is the first way to check if a vector field is conservative. So the second way to do it is to understand a property of conservative vector fields. So this one says that if we have a conservative vector field f, it means that we can write f as the gradient of a scalar field. The gradient of a scalar field. So if we can write f as the gradient of a scalar field, it would mean that it's a conservative vector field. So let me explain what that means. So let's just say we have a scalar field v, right? And then we take the gradient vector of that scalar field v. So we take grad v. And of course, the symbol for that is nabla. So we take the gradient vector of v. If that gradient vector is actually equal to the vector field that we are considering, it means that f was a conservative vector field. So let's just take our previous example. We had f being equal to 2xyz in the direction of I, plus x squared z in the direction of j, plus x squared y in the direction of k. So now what is the gradient vector? So we have some gradient vector v, and you know the gradient vector is defined as just the derivative of x in the I direction plus the derivative of the function, scalar function in the y direction plus the derivative in the z direction. Sorry, in the k direction. Well, it's the same thing. Derivative of the scalar function with respect to z in the k direction. So now, can we check if f is a scalar function that was found the derivative of, and carry on in that manner? So what we have to do is we have to integrate. So if we get a nice looking perfect integral, then it means that this was the case. So day v day x actually is now 2xyz. So if we integrate this, then we get that v is equal to x squared yz plus some function of y and z. And then we also see that the derivative of v with respect to y is equal to x squared z. So if we find the integral of this with respect to y, we see that it is x squared yz plus some function of x and z. And lastly, if we find the derivative with respect to z, we see that it is x squared y, and then integrating this with respect to z, what we get is x squared y z plus some function of x and y. So what do we see? We see that these three are basically the same. It's the same only if f g and h are equal to 0. We can see from inspection that this is the case. That means that we have some scalar function v, which is equal to x squared yz. And what do we notice? We notice that if we find the gradient vector of v, then we actually get our function f. We did that because we integrated and we checked that there is some scalar function that exists. When we find the gradient of that scalar function, we get this vector that we are considering. So this means that it's a scalar field. So if we integrate our vector that we're considering, and if it gives us a nice scalar function that we can easily see, then it means that, yes, this is a conservative vector field. So that was the second test. Now the third test is basically something that stems from the second test. So if we look back at our previous videos as well, we can see that we can take the curl of different vectors. You can remind yourself what the curl is. So if we take the curl of the gradient vector, remember that we just saw that we had a gradient vector, and if we take the curl of it, it means that we're taking the cross product between this gradient function and the gradient vector. And in the previous videos, we had proved that this is equal to 0. When we take the curl of the gradient vector, we get 0 essentially. And we have just worked with the gradient vector. So it means that the curl of the vector that we are considering, the vector that we are starting to see if it's conservative or not. So if we simply take the curl of that vector, and if it gives us 0, it means that it's a conservative vector field. So we can just easily see it in the example. So the example was f is equal to 2xy in the I direction plus x squared z in the j direction plus x squared y k. So if we take the curl of this, so we can just remember how we take the curl. We take the cross product. So we write I, j, and k in the first row. Then we write day x, day y, and day z in the second column. And in the third column, sorry, the third row rather, we write 2xyz, x squared z, and x squared y, the components of our vector. And we take the determinant. So when we do that, okay, so we block out the first row and first column. So we write I, that's what the value is in the intersection. So you have to take the derivative of this x squared y with respect to y. And then what do we get? We get x squared. And then minus the derivative of x squared z with respect to z. And that gives us x squared. And then minus, now we're looking at j. So we block out first row and second column, and we're taking the derivative of x squared y with respect to x. And what do we get? 2xy. And then we do the same thing of 2xyz with respect to z derivative. And what do we get? 2xy. And lastly, we do it with k. So it's 2x squared, so it's 2 times xz essentially. And then lastly, the derivative of 2xy with respect to y, we get 2xz. You can see that this entire thing just becomes 0. So this is the third way of checking if a vector field is conservative. So each of these ways can be done independently to verify if a vector field is conservative. So thank you very much for watching. In the last few videos of this series, we will just look at divergence theorem, Stokes theorem, and Green's theorem.